Hello.
Hello. Let us start. Now, the last class I have discussed started the principal stress. I'm just repeating what is principal. Here, first of all, what is principal stress? This is actually now in a body which is subjected to under stress by direct external stresses and direct external inner shear stresses. But it will be seen that even very complex system of loading, where there is different type of load stresses of different magnitude and different orientation and different type are acting over a single prismatic bar, there always exist three mutually perpendicular planes. The planes, mutually perpendicular planes, means planes which are perpendicular to each other. Three planes, plane which are perpendicular to each other. Means there will be three-dimensional axis, that is y, that is x, that is z. There are x plane, there are three planes here, xz, yz, and yx and zy. These three planes are mutually perpendicular. And imagining the same three mutually perpendicular planes which exist every sort of every type of loading, which are perpendicular to each other, and on each of which the resultant stress is wholly normal. These planes, resultant stress is totally normal. Means either it will act, resultant stress will be normal over xy plane, means it is along z axis, which is normal to the xy plane, on yz plane, which is x axis, which is normal to yz plane, and y axis, which is on normal to xz plane. These three planes are defined as principal planes, and normal stresses across these planes are stresses as principal stresses. The largest of these two places is called major, minimum, smallest is the minor, and third place is generally taken to be equal to 0 for two-dimensional axis. Means we have assumed that the stresses along x-axis is the principal stress, is the major stress, or maximum stress along y-axis is the minimum stress, along z-axis equal to 0. Now, shear stress is 0. We have defined in the last chapter that shear stress is 0 in principal planes. So we are assuming a place where the stress acting in x direction is sigma x, that is acting in the y direction sigma y, that is, and shear force acting in both these planes are tau. So here we know that if we consider a plane like this, I'm just telling you the same old thing again and again. Now, if we have, it is like this here, I'm just quickly writing it. This is a prismatic bar here. X is a sigma x is acting in the x direction, sigma y acting in the z direction, and shear stress tau acting in this direction in y plane as well as in x plane in this direction, where mutually perpendicular to each other. Now, here we know that tau theta, we are imagining a triangle in an oblique plane like this, which is making an angle theta with the normal plane. The tau theta, the shear stress acting over this oblique plane is tau theta is equal to minus half sigma x sigma y into sine 2 theta and tau psi cos 2 theta, where theta is the in between angle between this plane and the normal plane. And sigma x and sigma y, this is the sigma x stress acting in x direction, sigma y acting in the y direction, the tau is the shear stress acting in x plane and y plane. Now, we know the shear stress in principal planes or major planes are equal to 0. So we simply equate to tau theta equal to 0 here to find out the orientation of the plane, or half sigma x sigma y into sine theta into equal to tau cos theta, and tan 2 theta is equal to tau 2 into tau divided by sigma x and sigma minus sigma y. This gives us two values of 2 theta differing by 180 degree, or two values of theta differing by 90 degree. So it is available here. It is like this on this plane. This is one value of theta, and it is another value of theta here. This is, if we take the orientation here, and this will be from the normal, it is theta, and again, if we draw a normal here, and this portion will be like this. So this is the normal plane. This is the oblique plane. This is theta, and there will be the angle. If we draw a vertical over this line, over this plane, that will be also theta. So what we are having, there are two principal planes are perpendicular to each other, and as in figure, perpendicular to each other. So if we consider this is one of the plane acting here, and this is also one of the plane which is acting like this, which is so this is one of the plane and this is one of the plane. They are mutually perpendicular to each other, means they are in between angle is 90 degree, and one of them is on carrying the principal stress. Both of them are carrying the principal stress. One is major and one is minor. Now, this gives us these two principal planes are perpendicular to each other. So sine 2 theta from this equation is available here. If we go through this 90 degree triangle. So here 2 tau is the vertical and base is sigma x minus sigma y. So hypotenuse will be sigma x plus sigma y whole square plus tau xy 2 into tau whole square to the power half or to the power or square root. So sine theta 2 theta divided by square root of sigma x minus sigma y whole square plus 4 tau square, and cos 2 theta plus minus sigma x minus sigma y cos square sine divided by square root of sigma x minus sigma y whole square plus 4 tau square. The right hand side of all this equation should have the same sign, positive or negative, while you have to supposed to use it. Substituting values of sine 2 theta and cos 2 theta in this equation here, we'll get in the equation 2.20 is the equation here. We first this equation. If we put the value of cos 2 theta and sin theta in this equation, then the sigma x will take this particular form, sigma 1, 2, or this will take this form half sigma x plus sigma y plus half sigma x minus sigma y cos 2 theta plus tau sin 2 theta. If we put the value of cos 2 theta here, it will become half sigma x plus sigma y plus minus half sigma x minus sigma y whole square, because there is a sigma x minus sigma y. There is a sigma x minus sigma y in the numerator. So both together will become sigma x and sigma y whole square divided by square root of sigma x minus sigma y whole square plus tau 2 for tau square multiplied by half, plus minus tau 2 into tau square into here there is a tau here. So this tau is being multiplied with this tau. So this has become 2 tau square divided by sigma x minus sigma y whole square plus 4 tau square. Should be plus minus here and should be plus minus here, because both this cos theta and sin theta is plus minus. Thus, what happens if we add them together just and keep the plus minus here? The numerator will be the same, sigma x minus sigma y whole square plus 4 tau square, and denominator will be sigma x minus sigma y whole square plus 4 tau square. So this can be simplified by adding. This is exactly the square root of sigma x minus sigma y whole square plus 4 tau square. This is the square. So these three cancel them each other. Cancel this one is one of them will cancel, and this half square root of sigma x minus sigma y whole square plus 4 tau square will come as the numerator. So what we have, we are having two stresses, sigma 1 and sigma 2. Sigma 1 will be this half sigma x plus sigma y plus half sigma square root of sigma x minus sigma y whole square plus 4 tau square, and sigma 2 will be, this will be plus here and this will be minus here, half sigma x plus sigma y minus half square root of sigma x minus sigma y whole square 4 tau square. So this is the maximum stress, sigma 1. This is the maximum stress or major principal stress. This is minor principal stress. Unless you know by inspection which of the two particular principal planes correspond to major principal stress, it is necessary to substitute one of these values into the equation to find out which of the values of angles corresponding to the major principal stress. So we have to put the value of value of the angle, value of theta here and here, because we know from this equation the value of theta is available from here. So what we are having, we have to put the values here and to find out where the stress is maximum. That is the, and so from that you have to find for which values of the angle corresponds the major principal stress. Now, the maximum submissive or principal shear stress. In any complex of loading, maximum and minimum terminal stresses are the principal stresses and shear stress is 0. But shear stress is not always 0. Shear stress is also maximum in certain plane. So to find the maximum shear stress and its plane, which is a system, we have to consider the equation of shear stress in a plane again. So that is, we have to write down the shear stress here, tau theta half minus half sigma x sigma y minus sigma y sin 2 theta plus tau cos 2 theta. Next, to get the maximum value of tau theta, we differentiate with respect to theta and repeat equated to 0. So d tau theta divided by theta is equal to minus sigma x minus sigma y cos 2 theta. And here, if we take the here, this is the constant term, and but this is the function of theta. If we take its differentiation, it will become 2 cos theta, 2 theta. and this half 2 will cancel this 2. So this equation minus sigma x minus sigma y cos 2 theta. Here we'll get 2 sin theta and minus 2 sin theta. It will be 2 sin 2 theta. So if we put it here, it will be minus again, and 2 tau theta is equal to multiplied by sin 2 theta is equal to 0. So tan 2 theta will be minus sigma x minus sigma y by 2 tau. This indicates there are two values of tau theta differing by 180 degree or two values of theta differing by 90 degree. This is the maximum shear stress plane at right angles to each other. Thus, the maximum shear stress planes lies at right angle to each other. So, in the case of maximum shear stresses are lies at right angle to each other, same is the case of maximum shear stress planes, which are also right angle to each other, but they are not same. Now, tan 2 theta equal to sigma x minus sigma y 2 tau. Now, if we put it like this, as base is 2 tau and vertical is sigma x minus sigma y, and hypotenuse will be thus sigma x minus sigma y whole square plus 2 into tau whole square to the power to square root of to the power half, whole to the power half. Thus, sin 2 theta minus plus sigma x and sigma y, and minus plus sigma x and sigma y divided by square root of sigma x minus sigma y whole square plus tau square cos 2 theta plus minus 2 into tau square root of sigma y minus sigma x whole square plus 2 into tau square. But right hand side of both the above equations should have opposite signs. If one positive, another negative while using them. Substitute the value of sin 2 theta and cos 2 theta in this equation here, we'll have minus outside the bracket, the sign is minus half sigma x sigma y minus plus sigma x sigma y divided by sigma x minus sigma y whole square plus 2 into tau, and plus minus there is plus minus tau. Tau is sin theta. Cos 2 theta here, there is a plus minus here, not minus plus. So plus minus tau 2 into tau divided by sin sigma x minus sigma y whole square plus 2 into tau whole square, 4 into tau square. Thus, if we use this minus and with this minus plus, it will become plus minus. So both sides there is plus minus, and if we take this numerator, common numerator here, and add them together, then square root of sigma x and sigma y whole square plus 4 tau square is the denominator, and at the numerator sigma x, this sigma x multiplied by sigma y multiplied by sigma x minus sigma y, this becomes sigma x minus sigma y plus, and we take half common here, and tau into 2 tau is 2 tau square. If we take half common, and this will become 4 in the numerator, so 4 tau square. So both this numerator and denominator become same, thus it becomes plus minus square half square root of sigma x minus sigma square plus 4 tau square. So maximum shear stress is given by this equation. This provides the maximum and minimum value of shear stress. Both numerically are equal but opposite side. We know shear stresses are supposed to be equal to each other, but they will be acting opposite to each other. So their numerical value is same, but as they are acting opposite to each other, they are having one of them is plus and one of them is minus. The negative or maximum minimum value indicates that is a right angle to the positive value, as it is acting at right angles to the positive value. And these two complementary shear stress. The magnitude of maximum and minimum shear stress is given by half square root of sigma x minus sigma y whole square plus 4 tau square. Here there is no sign or there is plus, because we are taking account to magnitude only. The maximum shear stress is given via this equation, half sigma x and sigma y plus half square root of sigma x and sigma y whole square plus 4 tau square. And minimum principal stress is given as half sigma x plus sigma y minus half square root of sigma x plus sigma y minus sigma y whole square plus 4 tau square. So if sigma y1 minus sigma 1, we subtract sigma 1 from sigma 2, sigma 2 from sigma 1. So these two equations, these two sides will cancel each other. So this side remains 2 multiplied by half into square root of sigma x minus sigma y whole square plus 4 tau square, all equal to square root of sigma x minus sigma y whole square plus half plus 4 tau square. So this is equal to tau max. This is equal to tau max, half tau max, 2 into tau max. So tau max will be, this is equal to 2 into tau max here. As tau max is half square root of sigma x minus sigma y whole square plus 4 tau square. So tau max is, if you put tau max here, it is equal to half of sigma 1 minus sigma 2. So the maximum stress will be the half of the difference between the maximum major principal stress and major principal stress minus minor principal stress. The two principal planes are given by tan 2 theta 2 tau p 2 tau divided by sigma x minus sigma y, and the maximum principal stress, maximum shear stress is tan 2 theta 2s is equal to minus sigma x minus sigma y divided by 2 pi. That's the half, just opposite. That is, this is divided by half. This one divided by this this item is equal to gives us the maximum shear stress. Maximum plane for maximum shear stress. Now, if we multiply both of them, if we multiply this equation and this equation, then tan 2 theta p multiplied by tan 2 theta x s is equal to minus 1, which means 2 theta x plus 2 theta p plus 90 degree, or theta s plus theta p is equal to theta p plus 45 degree. Means theta of the angle of the principal stress into multiplied by 2 is equal to angle of shear stress multiplied by 2 is equal to angle of principal stress multiplied by 2 plus 90 degree. Or here minus 1 is 45 degree, or theta p and theta x plus theta p is equal to plus 45 degree. This indicates the planes of maximum shear stress lies at 45 degrees to the planes of principal stress. The above conclusion can also be drawn from the fact that in case of biaxial stresses on a rectangular element, discuss this section. In case of a principal stresses, no shear stress acts on the horizontal or vertical plane. Thus, sigma x sigma y denotes the principal plane in the element, as in the case of biaxial stress. The maximum value of shear stress in the plane is 45 degree biaxial stress. So sigma x tau max is equal to half sigma x minus sigma 1 minus sigma 2, or half square root of sigma x minus sigma y square plus 4 tau square. One important conclusion here we are having here. For biaxial stress, where there is stresses, biaxial stress means biaxial stress acting in x, y plane, but not in z plane. It's acting in two mutually perpendicular planes based on a rectangular element, say prismatic bar, in the what we have discussed so far over it. So if the stress is acting mutually perpendicular plane over a principal bar, then in case of a principal stress and no shear stress acting in the horizontal vertical plane, for principal stress, there will be no shear stress in this horizontal vertical plane. But sigma x and sigma y is not a principal stress in the element, as also denote principal stress in the element, as in case of biaxial stress, the maximum value of shear stress lies at 45 degree plane. So as the difference between the principal plane and plane of principal stress and that of shear stress is differed by 45 degree, we are saying that maximum value of shear stress lies in the plane at 45 degree. Then the principal stress and is tau max half sigma tau sigma 1 minus sigma 2 plus half square root of sigma x minus sigma y whole square plus 4 into tau square. Unless it is possible to know by inspection which of the two planes perpendicular to a particular direction of principal shear stress, it is necessary to substitute one of the values of theta into the equation and to find out which of the value of the angles correspond to a particular direction. So what we are, how we will know? First, you have to know, judge by the value, which is maximum, which is minimum. If still you cannot do, you have to substitute the value of theta into the equation, find out what is the particular value of tau theta. The process is same. Now, what will be the normal stress acting on this planes of maximum shear stress? We know sigma theta is half sigma x plus sigma y plus half sigma x minus sigma y cos 2 theta plus tau sin 2 theta. Now, if we plot here, half sigma x plus sigma y plus cos 2 theta comes outside the bracket, third bracket, and inside the third bracket it becomes half sigma x minus sigma y plus tau tan 2 theta, and half sigma x plus sigma y plus cos 2 theta, half sigma x minus within bracket, half sigma x minus sigma y minus tau, and tan 2 theta is equal to, or tan 2 theta is equal to sigma x minus sigma y divided by 2 into tau, which is we are showing the angle of, which here showing here with this using this equation 25, where the value of maximum principal shear stress theta sigma x minus sigma y divided by 2 into tau. So we put it here and put the minus here. So the equation takes this particular form where and this becomes equal to this tau is cancelling each other, and this half is common. It can block outside here, this half and this half. So that will become sigma x minus sigma y minus sigma x plus sigma y. So this portion is cancelling each other, becomes 0. So this remains sigma theta is equal to half sigma x plus sigma y. The direct stress acting on a plane, on an inclined plane, is half sigma x and sigma y. When for a for a plane of maximum stress, we have for a plane of what is the value of normal stresses, which is given by sigma half sigma x plus sigma y. But we have just formulated it by putting the value of cos tan 2 theta in case of maximum shear stress. Thus, the normal values of magnitude sigma x plus sigma y half act on each of the two planes of maximum shear stress. So, first we have to find out from this section, we have to find out what is the maximum and minimum principal stress and what is the angle of the plane with the normal over which this maximum minimum principal stress are acting. Next, we have to find out the plane as well as the plane where the shear stress, maximum shear stress is acting, and what is the value of maximum shear stress, and what is the relation between the major principal stress, minor principal stress, and maximum shear stress. Now, let us go through the next portion. This is defined as Morse stress cycle. So far, we have discussed the process of getting the principal stress and principal strain analytically. But there is the process of measuring, of calculating or measuring the principal and principal stress and stress by use of a graph, which is comparatively quick and easily understandable. How will you do it? This is called mode stress tracker. Now, how will you do it? Let us discuss. Say for two perpendicular direct stresses, instances what we have done, we have gone through for few instances that one perpendicular direct stress two perpendicular direct stress, shear stress, only shear stress, and two perpendicular direct stress, and one mutually perpendicular shear stress. Now, what happens? Let us first calculate the two perpendicular direct stress itself. What we have here, a plane AB over which the stress sigma y is acting, and a D by which the principal plane sigma x is acting. And we want to calculate want to find out the value of sigma x over a plane which is acting at an angle theta here, and tau theta which is acting normal to the plane BT. And that we are supposed to do graphically. What is the process? First of all, we have find out a scale. For plotting different value of stress. Next, first we have to find out. Next, we have to find out a plane, a origin O. Find out the origin. And find out the origin. That is O, A, O. Then on x-axis, we have drawn an x-axis from origin to the rightwards, which is horizontal. Draw x-axis. From O to rightwards. Now, on the x-axis, take OF, that is O into F, is distance equal to the value of sigma x. OF is equal to sigma x. Put the value of here as we find out the scale for plotting the different stress. According to the spread, write down, plot this length OF and OE as sigma y. This length is equal to OE, which is equal to sigma y. On the same scale, we plotted here. We got 2 points E here and F here over the x-axis drawn from origin O. Next, of the same stress is taken towards the right of the origin if tensile, and towards left of the origin if compressive. That is important. Both these stresses are positive in tensile, so we are plotting it to the right of the origin. Or if some of them is negative or compressive, we have to plot it from the left side of the origin. If both are negative, both are supposed to plot from the left side of the origin. Next, what we are doing, we are bisecting this length E into F. Bisecting this length in F at C. This is the midpoint is at C. Next, with the center at C and with the radius at CE or CF, we draw a circle here. The radius CF represents the plane AD. Yes, radius CF represents this plane AD, where over which the sigma is acting, and radius ECE, opposite to that, represents the plane AB in case of sigma y, which is a line of action of the plane sigma y. Now, the planes AB and ED, which are directed at 90 degrees, are represented at 100 degrees apart, or double the angle in Morse cycle. So as we know, all these angles are multiplied by 2. We are using 2 theta here. So here you have to plot the angle 2 theta here from the point here, from those side, and the straight line is drawn here. Now look at an inclined plane in this circle by making a radial line at double the length, which is required. The plane is given by the plane. That is, the plane BD is inclined to an angle with the plane AD in the counterclockwise direction. Then make mark CR at an angle 2 theta with CF in the counterclockwise direction. Here, AD, what you are doing, plane BD, this is the plane. It is acting. It is on angle anti-clockwise direction. This is from the normal. It is taken anti-clockwise direction. So here we have to, from the straight line, we have to draw anti-clockwise direction equal for a value equal to theta, 2 into theta. Now this straight line we are drawing here, which will intersect from this point here, and as well as this point here. Now drop a vertical RL and MS joining OR, which is intersecting 1. Now it will be shown that OR, it can OL and LR, O into L into plus O into L and L and LR represent the normal shear stress component lies on the inclined plane BD. From the geometric figure, OC is half OC plus OC, half OF minus CF, because OC will be the OF minus CF, that is OF, OC from here to here. One is OF minus CF, and another is OE plus CF. Another is OE from here to here plus C. So we are putting OF minus CF plus OE plus C plus half OF minus CF plus OE, same thing. That as if C is equal to CF, O plus CF here. So we are replacing C by CF. As seen here, that is CF and that is C. Both are the radius of the circle, so they are equal. OF minus CF plus OE plus CF is equal to OF plus OE. That is given by OF plus OE. If we take